distance. So if I want to scale color more than texture, texture, we haven't talked about that yet. All right, we'll do that next. Or color more than luminance, you make that decision ahead of time. So there's this parameter choice of window size, but there's also a general distance metric function choice. But you have that in every sort of clustering that you do. It doesn't make any assumptions about the shape of the segment in the image, or the cluster in the image. It just does this in the probability distribution of the pixels. And it's a very generic technique for finding multiple modes. And people use mean shift for a variety of things, like tracking, when we actually talked about doing that previously. As in anything else, there are some downsides. It does depend on this window size, and sometimes figuring out that window size is a bit of an art with respect to the nature of the set of the images that you're looking at. And the other problem is, because you are sort of moving in feature space, and you want to make sure that you get a reasonable number of points within your region of interest in order to shift for the mean. Well, suppose you've got a big feature space, right? And what I mean by that is you've got 50 dimensions. Well, almost by definition, your feature space will be sparse, right? Because the number of little, let's suppose you carved up every dimension into like 10 buckets. Well, if there's 50 dimensions, right, that's 10 to the 50th buckets. So by definition, there's going to be lots and lots of buckets that have hardly any points in them. So mean shift needs you to have a reasonable number of points within that region, so it doesn't work as well in high dimensions. So far we've been doing segmentation as clustering, and we've been using some feature space based upon color, and then we have these different algorithms. One of the challenges is that things like just color or the brightness or position, which is something else we looked at, alone are not enough to do segmentation. And here are some examples. So you can see that, generally in this area here, the colors are about the same as this area there. Likewise, the brightness here, the average brightness is the same as the brightness over there. Now, you have no problem seeing the differences between these, but that's because you just don't use brightness, position, color. You also use texture, right? Obviously, the texture here is different than the texture there. Likewise, on the fawn, the texture there is quite different than the texture here. So the question is, how would we introduce some measure that was sensitive to texture into our segmentation? One way of thinking about texture is this. So here I have this picture, okay, and I've got clearly different texture here than I do here and I do there. All right. So here is one approach. Let's compute a series of filter outputs. So here's it 1, 2, 3, 4, 5, 24. It says 24 right there. Here's 24 different filters. Okay, and they may have different orientations. So here we get different orientations. And they have different scales, so they go from a coarser scale to a finer scale, and here's ones that are just sort of little center surround. It almost doesn't matter, well, it does matter, but it almost doesn't matter which filters you use. The idea is that you're creating a new set of dimensions that you'll have for every point, right? And when you do that, the idea is that hopefully along these different dimensions, and there's 24 of them, however many you have, you would get some clusters depending upon the types of textures that you have in your image. And that's what's being shown here, right? Is you have these clusters in this image space, all right? And so here's an example of using, let's just suppose we take a look at, this is the derivative in the x direction. So how much gradient there is going in the x direction at one particular scale. This is one of the dimensions. And this is in the y direction, so it's measure your gradient in the y direction. And the idea is that, well, in this case, there are little areas that have, in this case, windows that primarily have vertical edges, right? Because they've got strong x gradient and no y gradient. Likewise, here's horizontal. This has a little window that would have a texture in both of them, and these would be areas that have hardly any gradient at all. And what we're going to do, actually, is do clustering twice. The first thing we do is we're going to cluster in that big feature space I was just showing you. And those clusters are going to be referred to as textons. Now, this is a word, I think it's a word that was coined by Bela Ulic, who was a psychophysicist, guy who did random dot stereograms quite a while ago. And they were referring to things like T-junctions and little end stops and other textural descriptors that existed in images as sort of he saw them. And the idea is that these clusters in the feature space would be different little textural elements that were found in these images, right? And so you would describe each little window, okay, by what's referred to as its text-on histogram. That's what this thing is going to be showing here. We'll take a little bit more of that. But the idea is that here there is just a single value at every pixel, which is the single text-on that tends to be present at that pixel. That is, which cluster it got mapped to. And you can see that, you know, if you were to just cluster based upon this, it would be kind of weird because, yeah, this is not one nice thing because it's a single texture. But the idea here is that even though this is a single texture, there are all these different little textons that are present. So instead of segmenting the image based upon which single cluster you're mapped to, instead what we're going to do is we're going to take little windows. So here's a little circular window, and we compute its text-on histogram. Okay, so now we've got a whole bunch of different textons, and this is the count of the number of those textons. So I get a histogram at every window. So here's another window, and it has kind of a similar histogram. And here's a third window. Well, its histogram looks nothing like that. And the idea is that you're now going to cluster in the histogram space of these textons in order to be able to get your segmentation. All right? And how well does that work? Well, let me show you an example. So here is a picture of a rhinoceros. No, a zebra, I guess. I don't know. Thing with stripes. Okay? So suppose I cluster it based upon color. What would that look like? Well, it would be a mess. Okay? And there's your mess, color-based regions, and you'd say, well, that's a terrible idea.
That's a terrible idea.
So what would be a better idea? Well, how about we cluster based upon texture? And you can see that you get these broad clusters that seem to do, you know, reasonable job. I mean, it does make the entire, you know, this region here, which is sort of this big region there. You'll notice that it's not, you know, because of the scales that got used, in this case, it didn't find these legs here or this one there. But that's a function of sort of how you go about describing it. And I will say that in general, this is kind of an under-segmented result. There probably should be more segments. But clearly, this is way better than this color-based approach because it allows us to describe the texture. We've seen two methods for expanding our ability to do segmentation. One was the new method, the new algorithm of finding modes within some feature space. And it was, you know, didn't require you to know the number of modes to begin with and all these other properties. And then in some sense, more importantly, no, not more importantly, in addition, we found a way of expanding our feature space to include something that describes texture. And what you did was you created a big feature vector, texture feature vector at every point. And you would cluster that to get these keywords or these textons, and then you would, for every region, you would get a histogram, and then you would cluster based upon those histograms, and that's what gave you your segments. Combined, these gives us a pretty powerful method. Welcome back to Computer Vision. We're going to continue with our conversation about segmentation. And this time we're going to up a little bit the sophistication of some of the methods that we're talking about. So far, all of our segmentation work has really talked about sort of clustering pixels within some feature space that is sort of describing each of the pixels. So I might build the clusters in position and intensity, or position and color, or even in the texture space. What we didn't really do was talk about the connection between one pixel and another. Right? I mean, after all, if you're doing a segmentation, the idea is that you're going to be drawing a boundary. You're going to say, nope, you go to the left, you go to the right. So I want to talk about the connection between pixels. So to do that, we have to think about pictures as of not just a collection of pixels, but actually as a graph. And what I mean by a graph is shown here. So in the graph, we have a node for every pixel. Okay? And between every pair of pixels is a link. Okay? Just as in any other graph, those are the edges of our graph, right? And on each edge, there's what's referred to as an affinity weight, or just a weight. And here that's written as WPQ, right? And the idea is that I'm going to need an edge for any weight that is non-zero, okay? And the weight is going to measure the similarity between two pixels. And the similarity will be essentially inversely proportional to the difference. So that just means that the more different they are, the less similar they are. And another way of saying is if the difference is too big, I'm going to say the similarity is 0, so those edges go away. So I'm going to build a weight matrix using this affinity. So a standard affinity, for example, might be that I'm just going to use a Gaussian, right, where I say the affinity between two pixels, I and j, is just this exponentiation. As a function, it's just this exponentiation as a function of the distance. So of course there is a parameter here, and here you can see the change in affinity. Depending upon what that parameter is, you get these different curves. And essentially, if you use a very small sigma, this thing grows quickly. So in which case only nearby pixels get any reasonable affinity at all. Whereas if you have a large sigma, you can have strong affinities even between points that are somewhat far away. Far away in your distance space. So if your distance includes just color, then it would be that. But typically, our distance is also going to include actual distance. So if I have this graph, segmenting the image is just breaking the graph into segments. So here I'm showing you that I took all those points I had before, and I broke this thing into 3 segments. So that would mean that there were 3 regions in this image. And the idea is that what I want to do is I want to delete links that are between the segments, right? So maybe there used to be a link that connected this point to that point, and it's been broken, all right? So I'm going to delete links that go between segments. And so which links should be easiest to break? Well, obviously those with the lowest affinity, right? Because if I break them, they're saying, you know, the blue pixel and the red pixel, which maybe have a great distance in my feature space, so they have a very low affinity between them. By the way, here's an actual example of segmenting this tiger against the background, and you can see that it's got spatially contiguous regions by doing that. So what I need to do is I need to construct a distance function such that similar pixels will end up being in the same segments if they're nearby, and dissimilar pixels, ones that are very different, will end up in different segments. Now, many of you, because this is a graduate course intended for computer science, I'm going to assume you've seen some form of an algorithms class, and you may have heard that there's something called a graph cut algorithm. And a graph cut algorithm does exactly what you think. It cuts a graph. So here I've got a graph, and the idea was originally it had lots of connections in it, and when I'm all done, I've decided to break this graph on those 4 links to create 2 different graphs, A and B, and they're totally disconnected. So those would be 2 segments in our image. And the idea is that the cost of a cut is quite simply just the cost of all of the segments that you broke. So that's what this thing shows you here. I take for all of the, if there's a P in A and Q in B, and I've separated A and B, what's the cost between all of those? And a graph cut would give you a segmentation of the image. So the question becomes, what is a good graph cut, and how do you find one? So there are algorithms called min-cut algorithms, sometimes called max-flow, because they're duals of each other, they're the same, that allow you to find that segmentation in a relatively not too complex a manner. Fast min-cut algorithms exist. So the original min-cut, Folk and Fulkerson, you may have learned. There are subsequent more rapid ones. We're not going to go into those here. All you need to know is that you can go to your local algorithm store and buy yourself a good graph cut algorithm, and the more you can spend, the faster a graph cut algorithm you can get. And the idea is that that would partition your graph. A problem, though, if we just use min-cut for doing segmentation, is that min-cut, by definition, is going to try to pull out little segments that have as few connections as possible. So what it tends to do is it tends to pull off very small little segments, because by definition, a little segment will only connect to a small number of other nodes. So really what you want to do is you want to do something a little bit smarter than that. And in fact, what you want to do is what's referred to as normalized cuts. So normalized cuts fixes this bias that min-cut has of wanting to pull off these little elements. And the way it does it is it's going to propose a cut, and it has the traditional measure of cutting A and B, but it's normalized by the association within A and the association within B. And a simple way of thinking about it is the association